Hi, this is Garrett McKenzie, the owner of Plastic 411. I'd like to welcome Plasology to this webinar on the do's and don'ts of building a robust process. So first, let's go ahead and define what is meant when we refer to a robust process. A process is a series of actions or steps taken in order to achieve a particular end. Then robust is strong and healthy or vigorous. So when we refer to a robust process, we're referring to a series of actions that lead to a strong and healthy production event. So now we must ask, when is a production event strong and healthy in plastic injection? Well, there's four primary measurables that we must first look at to find the success or failure of a production operation. The first would be efficiency, state of achieving maximum productivity with minimum wasted effort or expense. We also have downtime, which is mold changes, color changes, maintenance events planned or unplanned, and also poor planning and scheduling. In addition, we have yield, and that's going to be the total parts produced after scrap, which also affects efficiency. And then, of course, we have quality. And here we're going to be talking about molded in quality because we don't want to confuse that with sorted in quality. So these four measurables can be monitored and enforced even further by requiring that our process demands meet or exceed quoted cycles. We're going to minimal downtime. It needs to be repeatable between mold changes. Our mold changes need to be fully standardized. We need to eliminate fluctuation in those times so that we have more control. And our startups need to be controlled with minimal scrap, ideally 2 to 3 parts on startup. Our total scrap produced during each production run would preferably be 0, not counting startup scrap, but no more than 1.5% of total production. And as stated before, maintenance events need to be planned, not unplanned. What that means is, just for instance, if we're running a tool and the mold breaks and we're thrown into a setup that we didn't expect to do, well, that would be unplanned, where preventative maintenance events would definitely fall under the planned category. So now we must ask, how do we get from the development of a part to point B, which is a stable, repeatable process? And this is going to achieve fast and reliable part-to-part changeover times. We're going to have a molding process that quickly starts and offers optimized efficiencies, 0 to low scrap and high yields, and most importantly, production longevity. We want little to no production hiccups, adding to our downtime. So when we're talking about this, the definition of efficient best describes our approach to developing these type of world-class manufacturing systems. So efficient, especially of a system or machine, is achieving maximum productivity with minimum wasted effort or expense. And in addition to that, we want to prevent the wasteful use of particular resources. So therefore, process efficiency is accomplished through a series of actions or steps that we take in order for us to maximize productivity, and we want to do so with minimum wasted effort or expense. So the next question would be, what are the steps? Well, this is where we need to not put the cart before the horse. We need to outline the steps, and we must first establish the engineering phases that occur before a job is actually turned over to production. Those phases are mold design, tool building, press setup, process development and optimization, and also very important, process control. So these phases are all critical components of a robust process. Poor handling of any phase affects our ability to build strength into our end result. So let's break each phase down and analyze what each needs to accomplish. My primary focus will be on the processing side, but I will briefly touch on design and building. So in regards to mold design, the biggest thing to point out is it's best served as a team participation event. So basically, during the design process, the designer, the mold maker, and process engineer should be completely involved throughout the development and very close communication. This valuable approach helps to prevent major headaches at the end once the tool is used, such as a mold that is difficult to process or a design that is difficult to build. So then we reach the mold building stage, and some of the important characteristics of this stage is we want to assure that the mold is cooled and heated properly. And in addition, we're going to verify that the movable half has enough support pillars to prevent flexing, because we want to prevent situations where we end up with flash because the mold easily flexes. In addition, we want to validate that the mold has been sufficiently vented, and we're also going to want to assure that draft has been added to areas prone to drags and sticking. A lot of times this will come out when the tool is initially sampled. In addition, we're going to start recording our gallons per minute of individual circuits, because we're going to start getting baseline data for comparison, or historical data that will be used later in the future to assess whether changes are happening with a tool that need to be addressed. Another thing that we're going to record is we're going to record a supply and return pressure of individual circuits for baseline data. And we're also going to record hot runner manifold steel temperatures for baseline data for comparison when we run into problems. So now we get to setting up the press, which setup is, of course, one of the most important phases of the engineering stage. It's very important that we get ourselves in a situation where the setup is completely standardized and everyone is able to complete the mold change in exactly the same way without a lot of individual approach. We want the mold set exactly the same way every time. So basically, we want to standardize the setup to assure that it's installed exactly the same way every time. We want to develop methods of quickly centering and leveling the mold. We want hard plumb tooling to assure cooling is repeatable. We're going to dummy proof our connectors, water, hydraulic, and electrical, so that they're hooked up exactly the same every time. Then we're going to standardize our knockout length whenever possible, and also we're going to standardize the bushings. In addition, we're going to look for other ways to eliminate waste of motion. So we want to maximize our changeover efficiencies to make changeovers quick and consistent. We need to plan and prepare for each change prior to the event. And we're going to look for tools or approaches that can make changeovers faster and easier. It's very important to take advantage of the strengths and skill sets of your entire production crew. You want to use your people that have strengths to train the people that have weaknesses, because the stronger your team gets and the reduction in whatever your weakest links are, this improves your ability to control. And you also want to make sure that all the tools are provided needed to complete the job. Situations arise where tools are being searched for, tools that you need are not there, so other methods must be used that take more time. You want to eliminate any time from your setup that you don't need. And another important thing is to use time studies in regards to your setups to identify problems and weaknesses. Quite often, the time study will give you tools that you can use to improve your setup time and reduce your downtime. You're also going to want to develop your production operation to be operator friendly. You want to verify ergonomics. You don't want your operators having a lot of waste of motion, because in order to maximize your cycle time, you need your operator situation to be maximized. You're also going to want to provide instructions that clearly communicate direction. An example of this, I had a plant manager once who called a meeting, and he held up a shampoo bottle, and he pointed out that there were directions on it that said lather, rinse, and repeat. And he asked us, he said, why do they have directions on this shampoo bottle? Well, nobody could answer the question. He answered, it's because somebody held the bottle up and said, what do I do with this? The point of this is that we want our operators to fully understand what is expected of them and what procedures need to take place. This is going to give them the tools that they need to adequately perform the work and give us the best effort possible. In addition, we're going to want to provide visual aids whenever possible. Area setup would be one situation. Another, if you have recurring scrap events that are occurring, and you have samples of those defects, then you can put postings or samples of the reject at the press so that the operator is available, or has that available to them, and are aware of the situation. In addition, it's important to let your operators have a voice. Your operator is the only person that looks at 100% of the parts 100% of the time. And quite often, when it comes to the actual procedure of what they need to accomplish within their production stage, they're the ones that know what the actual problems are. And quite often, they can even give suggestions as to what can be done to improve their situation. As always, I'd like to point out that fast cycle times equals less time to inspect. It's important to, whenever possible, do a time study and make sure that your operator has adequate time to inspect the parts, because rework is more costly than being able to inspect each part individually and having the time to do so. In addition, we want to look for ways to remove human error from the process. So now we're going to talk about developing and optimizing process. So earlier we defined that what we needed for a stable process was a molding process that quickly starts, offers optimized efficiencies, zero to low scrap and high yields. Now in the processing stage, we're going to want to add dimensional stability and repeatability. It all comes down to what steps are taken to both identify and then clarify the new process. So let's envision this ball pit as a multitude of potential processes. Each of these balls represents a single process, both good or bad. So now let's say that the only yellow balls are good processes. And as you notice from the pit, there's more than one yellow ball, because yes, it is possible to have more than one good process. Our goal is to find the best process. So imagine standing at the edge of the pit with your eyes closed and reaching in. That's what we're doing when we're trying to develop a process. We're reaching in and we're looking for that perfect process with a high production, low scrap, high yield. And we keep grabbing balls or grabbing processes, and we'll grab a red, we'll grab a blue. Those of course are not good. And then eventually we finally get to that yellow ball, which is our good process. Now this is the point where we need to record every condition that was needed to over and over grab that same yellow ball, or in other words, to use that same process to be successful every time that we start up and have repeatable success. So in a nutshell, a robust process has been validated as profitable and repeatable. Now, the general process validation rule that I follow is whenever I get a process and it's running 100% efficient, 0 to 1.5% scrap, and high yield, at that point I record all data. And by repeatable, what we're talking about is that you need to be able to run that, set up that process and run it over and over. And every time that you run it, you get a quick start and high productivity. So following validation, you're going to do a snapshot of sorts through process recording involves setting and monitoring actuals. This is what's going to help to assure that the next time the press is set up, the process can be repeated. It also develops a standard of recordable data that can be compared historically, which helps to identify changes within the core molding system. The more care we put into documenting every recordable condition from a previously successful run, the easier it becomes to repeat that process. So the first steps we need to take, it's absolutely crucial that shot size be established using decoupled molding procedures. We want to ensure that parts are filled to 95 to 98% with no pack or hold pressure. And once this has been established, we then add hold pressure back into the process until part aesthetics and dimensions meet the established criteria outlined by our customer. It's important to note that there are several important process studies that are also a part of establishing a robust process. Performance of this testing is a critical part of every process foundation, and these studies include. So the first study we're going to look at is a viscosity curve study, and this particular study is it's a viscosity curve for polyethylene at 175 and 220. The first data points are under the black at 175, and then the red is representing the 220 degrees Celsius data. A couple things to note. The slower the injection speed, the higher the pressure. That would be because with the faster speeds, we have a lower fill time, so the material is thinner as it comes to end of fill. And then the second thing to note is when you make a comparison of the data points for the one at 175 and the data points at 220, 220 is a lot lower because you have a higher temperature, which means a lower viscosity. Another important study would be cavity balance, and as you see here, we are basically measuring 16 cavities. Then we're recording the average part weight for each. This would be based on a sample lot. It could be a sample lot of 5 or 10, even 25 pieces. And then we're going to basically add our average part weights together to come up with a mean, and then we are going to calculate what the degree of imbalance is by a percentage. And parts that are at the low end, we would open up the gates in order to improve the balance, and our goal would be to get the part weights be consistent across all 16 cavities. This helps us to basically, when we're injecting plastic, the plastic flows evenly across all cavities and gives us better process control. So this would be one of our most important studies. It's the gate seal study, also called gate freeze, and we're establishing hold time. As you see, they've recorded 10 data points and times ranging from 10 to 19 seconds. Now, what's important to note is there's a fluctuation in the weight as you increase hold time, and what you do is you keep adding a second, so 10, 11, 12, 13, 14, 15, 16, 17. And if you look between 16 and 17, the part weight has stabilized. What that tells you is that at 16 seconds, that is when gate seal is actually being established. So you would set your hold time at 16, and then you know that that portion of your process has been standardized. We also have fill time studies, and there's a number of different ways of recording these and reasons why. In this particular one, they're actually measuring a difference in injection pressure at multiple fill speeds. Now, originally they were using a machine pressure transducer. That would be the data that you're seeing in the purple. On the left-hand side, they're measuring pressure, then they're measuring the actual fill time at the bottom. Well, what concerned them was when they went to a third-party pressure transducer, the data totally changed. As you can see, it's a lot lower. This isn't particularly a concern as long as the parts are still validated as true as far as aesthetics and dimensional stability. But what needs to be noted that at this point the previous historical data is no longer valid, and you would actually start new data using the new component. Another important one would be a design optimization experiment. It's also known as design, or DOE, excuse me. Now, in this particular experiment, they're doing 20 tests. They are ranging barrel temperature from 333 all the way to 417. They're going with higher and lower cooling times, and they're also going with higher and lower hold pressures. Now, if you look off to the right, they're evidently doing 3-part samples, and anything that you see that is blank, then evidently that did not work. There was a defect or something that made that measurement not work for this. So they're only going to save the ones that actually have the data for the part weight. Now, it's important to note that anytime that you make like a barrel temperature change, such as the 333 to 350, you're going to basically shut the press down. You're going to make your change to your 350 straight profile. Then once the temperatures come up and stabilize at 350, then you're going to restart the press and run it for 15 to 20 minutes so that you can get a heat soak condition to see what your parts are going to look like. Something else that should be noted is that oftentimes when you're making this type of multiple changes, it's a good practice to drop your shot size to 80%, make your changes, and then add shot size and reduce cutoff to get back to a full part. So the key to any successful molding operation is recording all data that's available when the process of producing minimal to low scrap is running at optimum efficiencies. By replicating these variables at machine start, you assure that you're repeating your previous run. So here are factors available that can be used to monitor your process. These are your process monitoring variables. So this is our data controls, basically our process monitoring data. The first and one that I watch the most would be fill time, and that's the amount of time taken from the start of injection to the point of reaching cutoff. It needs to be consistent, and it's a good way to, if you're moving a job from one press to another that has the same barrel size, then this is going to be one of the ones that you definitely want to repeat. And peak pressure is the other. That's going to be the maximum pressure achieved at the point of velocity cutoff prior to dropping off into hold pressure. Another key variable would be your running mold temperature. This temperature should be measured at various points in the mold, and it should be done with a mold in a running state. I like to give it at least 30 to 60 minutes of running before I take these measurements. And you're going to measure the individual cavities, the runner system, the bushing area, and etc. And you're going to record this data, and it'll be kept with your historical data. In addition, you're going to look at screw rotate time, which is the amount of time it takes for the screw to recover. In most cases, recovery would complete about 2 to 3 seconds prior to the end of cooling time. And you're also going to watch for variability. You don't want your screw rotate times to vary too much. If you're seeing big swings, then it's possible that your material's not feeding well. Another key would be your melt temperature, and this is the actual temperature of material as it exits the nozzle tip. You can also measure melt temperature coming through the hot runner. The measurement should always be taken with a barrel in a running state, so you're going to want the press to run for 30 to 45 minutes before you actually take a melt temperature reading. This will assure that you're consistent. Another key variable is, of course, your cycle time, and that's the amount of time taken for each shot to be produced. Now, variance should be minimal. If you're seeing big swings in your cycle time, you might want to look at mold and injector speeds. You might also look at screw rotate time. And then we also need to monitor cushion, which in most cases cushion holds steady between 0.20 and 0.35, which would be 6 to 9 millimeters. But on larger parts, 500-ton press and bigger, you might see bigger cushions. Other data controls that we're going to watch is we're going to watch the water pressure to and from process. And to process is, of course, your supply, and then from would be your return. And the reason you do that is you want to look at the pressure drop. For instance, if you have pressure going in at 50 psi and then the pressure coming out is 40, well, then you know that the water is passing through pretty freely, little restriction, good flow. Now, if you had the same condition of 50 psi going in, but the pressure drop, the water coming from would be at 20, then you know you've got pretty serious restriction and you might need to make some corrections. Something else you're going to look at is your barrel temp actuals, and you make that comparison to your set points. One situation that might arise where it's a problem is if you're in your metering zone, your temperatures are running 20 degrees higher than what your set point is, then you know you might need to make adjustments to your feed zone, the first zone, and to the set points of your metering zone, because you want those temperatures to be very consistent. Something else that would be a recordable is your back pressure actual, and you're going to want to check your actual pressure held during recovery stage, and then you can use that as a comparison as far as historical data. In addition, you're going to look at your material moisture. Quite often, one of the first things I would check if I had a splay condition and it was a full-out splay condition, not all over the part, then I'm going to measure my material moisture to make sure the material's been properly dried. Something else that's important as far as data control is your regrind percentage. You want to control regrind usage to assure the process variance is minimal and consistent, and it's important to maintain your regrind usage through proper blending or re-extrusion. Now, some other key points in robust processing systems, and we're just going to revisit melt temperature because it's a key variable that's often overlooked. Once a process has been validated, the melt temperature should be recorded. So let me tell you the process validation rule that I followed. Generally, once a process is run for 8 hours with 100% production, 0 to 1.5% scrap and high yield, then I would record that process as far as the process set points. Now, the next time that that process runs, I would run it at the set points that I had originally. If I'm able to repeat that process, then at that point, excuse me, I know that the process has been validated, and that's when I'm going to take and record all of my historical data, including melt temperature. Now, when heat-related defects occurred, that would be one of the first things I would check also. I'd be checking the melt temp prior to making any process adjustments. Basically, a validated process should not require any change. Process parameters should be able to be repeated each time a mold is set and started, as long as the setup was standardized. And before you change anything on your process, it's important to look at your monitoring variables first. You want to look at what changed. There's been a number of situations over the years where I've had a process that was validated for 6 months and something goes wrong and a young processor is trying to make changes to the process, but they haven't done the first step, which is to look at what exactly changed, because in most cases, if that process is validated, then something changes in the molding condition. There's no reason to change the process. So as a comparison, if the fill time is slower, you're going to look at your temperature actuals, your pressure limits, etc. I mean, there may be times you need to change your process to correct the molding condition, but you always want to check for mechanical changes first. You're going to confirm that your machine, material, mold, and auxiliary equipment are correct and functioning properly before making process changes. You're also going to want to monitor your molding variables for significant fluctuations. For instance, a cushion that varies sporadically can be a sign of a worn check ring or barrel wear. Barrel temperature fluctuations can point towards bad heater bands or thermocouples. And you're also going to want to consider recent mechanical changes made while servicing a press and whether they might be impacting the validity of your process. In addition, you're going to want to verify that the setup has been performed according to standardized procedures. This quite often in startup is going to be one of the first things you want to check. You want to make sure that the setup was completed properly. In addition, you're also going to want to make sure that your tools are cleaned properly, no less than once per shift, and materials such as nylon that are prone to gassing may require twice per shift. Your molds definitely need to be serviced. Slides and guide pins should be lubed, but it's also important to remember that over-greasing can be detrimental to your process efficiency. For instance, if you've over-greased and the grease ends up getting into a vent, then your gas might not be escaping properly because the tool was poorly serviced. And anytime you make a process change, before you make a change, you're always going to clean the mold first. Defects could be directly related to dirty vents or components. And as we said before, a clean and well-serviced mold is imperative to any successful molding operation. Well-serviced, an example is a situation where you might end up with unplanned maintenance. If the mold hasn't been serviced and components dry up and break, well, now you've got to pull the mold, send it to the tool shop, and now you have an unplanned setup, which is definitely going to slow down your changeover time. Now we're going to touch shortly on the best approach to introducing virgin regrind into your molding equation, because you really need to treat it as a different material. So initially you're going to determine the optimal virgin to regrind ratio, and then once you've established an effective blending process, you're going to record the process separately from a virgin run. What's important to note here is that the molecular chain of regrind is much shorter, and because of that, the viscosity is going to be lower. So the more regrind that you add to your production run, the faster your fill is going to be. So you're going to have to make adjustments to your process based on that change. Now, if your regrind percentage is fluctuating, then you're really not going to have good control. Something else you can do to gain further process control is you can re-extrude your regrind with virgin base. That makes the pellets themselves consistent, and this will help reduce the potential of inconsistent material drop-down rates. It's really important to understand adding regrind to your process changes material response. In some cases where aesthetics and dimensional stability are imperative, extruding your regrind while adding base would probably be a viable solution. And you're going to establish a separate process for the virgin and the blend to ensure that repeatability is achievable for both. So now we're going to go into process optimization. As we all know, lean manufacturing is a primary driver of profitability, and without lean, organizations find that their operations are sluggish and ineffective. This affects both the company's ability to grow, and the ability to take on new work suffers because systems have not been effectively streamlined. If you can't control the workload that you have, it's impossible to take on more work. So one of the first points to address under this topic is that it is possible for machines to run too fast. Every molding job is different, and basically the following conditions must be satisfied to be sure that the optimization is successful. So first and foremost, quality is the key to the integrity of every molding operation. So running too fast to provide adequate operator inspection defeats the purpose of effective production. Rework and scrap reduce productivity, so we need to take steps to assure that quality is not affected by optimization. For instance, if we were running 1.5% scrap, but then when we knock 3 seconds off the cycle, now we're up to 4% scrap. Well, evidently the optimization did not work. In addition, we do not want to sort in quality, we want to mold in quality. So if parts are being rejected by quality and having to be reworked because we made an optimization change, well, once again, we've shot ourselves in the foot. We're always going to want to keep our optimization tactics real, and as we make adjustments, we want to consider potential failures that could occur while doing the optimization. For instance, knocking 10 cents off a job molding nylon parts would be great, but we're going to have to remember that a lower cooling time increases our shrinkage, and it could potentially throw parts out of spec dimensionally. And in addition, during the optimization process, we want to be vigilant, and we need to make adjustments slowly. Anytime that we make changes to the process in clusters, we want to make everybody aware that we're making the adjustments. We're going to allow ample time for changes to take effect. We're going to keep those parts separate from our production and treat it as a sample. The sample parts will then be provided to quality for part layout and inspection. And then we're going to put the settings back until the parts and process have been validated. As I said earlier, sample runs should always be run separate from production. This keeps us from sending suspect or defect parts to our customer. So the following list outlines many of the parameters that can be considered when reducing the cycle time of a molding operation. So first, one of the easiest avenues is cooling time. And in most molding scenarios, the cooling time can be set about 1.5 to 2 seconds longer than the screw rotate time. There are situations where you might have to go with a lot longer cooling time, such as shrinkage or dimensional issues, but in most cases, you're going to want your cooling time to be set 1.5 to 2 seconds longer than the screw rotate. And dimensional requirements and parts sticking or other situations where you might need a longer cooling cycle. Hold time is another major contributor to maximizing cycle time, and as we covered earlier, the best method of accomplishing this is through a gate seal study. And then one of the biggest helps that we can get are from melt and mold temperature. First of all, the MSDS, your material manufacturer, provides you with a melt temperature, and as a standard rule, your melt window is going to be 25 degrees below that melt temperature. So if they give you a melt temperature of 500 degrees, then you know you can go as low as 475, and that's where you're going to start. In addition, your mold temperature, if you know that your mold temperature can start as low as 120, then you're going to start at the low end on both melt and mold temperature. You're basically going to raise temperatures in modest increments until you achieve process stability. And it's important to remember that higher viscosity of a lower melt temp could lead to defects. You might see problems with jetting, or you may even see a problem with burns because the thickness of the material as it knits causes shear, so you might have no choice but to raise temperatures. And then there's situations where part dimensions or aesthetics may require a higher or lower mold temperature. Good, for instance, would be a glass-filled nylon. A lot of times you have to run at a higher mold temperature to get good part visual quality. But the primary thing to remember is that the key here is to be a minimalist. You want to start at the low end so that you can try to keep your cycle time low, and then add back in to get a premium part. And using minimal temperature helps reduce cooling time, which also helps improve cycle time. Mold and injection speeds are another place where we can maximize and increase cycle efficiencies. When you're looking at mold open and close, you're looking at mold breakaway, mold close speeds. But you want to remember that they're affected by the complexity of slides, horn pins, etc. So as always, you want to keep safety and care for your mold to be your first priority. Added to that would be your low pressure close settings. You want to keep those as low as possible for mold protection. You also can look at ejection. Proper improper ejection setup adversely affects cycle time. If you're adding strokes to your ejection because parts aren't falling properly, well, that of course adds to your cycle. Or if your ejectors are being maxed out as far as eject forward, that also affects cycle. You also want to look at your ejection speed. Basically, when you set up ejection, you want to use only the amount of stroke you need to remove the parts safely and to prevent sticking. Basically, maximizing your mold open and close speeds helps you reduce the mold open time, which improves your cycle time. In closing, lean manufacturing requires continuous improvement and maximized efficiencies. When cycle optimization is complete, the resulting process will produce the highest yield, minimum to zero scrap, and minimum downtime events. It's important to remember that a true processing regimen continuously evolves, improving upon itself. We're always looking at our process and trying to figure out if there's other things we can do to optimize and improve upon the processes that we develop. By applying the steps outlined, we are able to achieve full efficiency while maintaining world-class quality parts. This ends my presentation. I'd like to thank you for your time and watching this webinar. If you have any questions, feel free to ask them now, or you can email me, Garrett@plastic411.com, or also you could email training@plastic411. In addition, you may call me at 404-793-9834. And now I will take your questions.
Dragging